This is our Milky Way galaxy, and within it is our Earth, the Sun, and practically all the stars that we can see with the naked eye. At the center of our galaxy lies a supermassive black hole known as Sagittarius A. But if we now ponder the history of galaxies and black holes, what do you think came first? The black holes at the centers of spiral galaxies, or the galaxies themselves? At first glance, everything might seem straightforward, but what if I told you that galaxies and black holes actually appeared simultaneously? Would you believe me? That's why let's try to understand this today and figure out what really came first. To answer this question, we initially need to understand what the universe looks like on large scales. Currently, the universe contains over 1 trillion galaxies arranged in a web-like cosmic structure. Within this structure, there are superclusters, intersections, and vast empty spaces, spanning tens of millions of light years. The observable part of the universe extends for 46 billion light years in all directions from the observer. However, it wasn't always like this. Once upon a time, the universe was much smaller, and it only began to resemble its current state after billions of years, thanks to the expansion of space. But now, it's important for us to conceptualize the universe on large scales in order to answer the question about black holes. Even though these topics may seem unrelated at first glance, I'll explain why they are crucial. That's because when we ask whether black holes or galaxies came first, we are essentially asking whether the universe evolved from small structures to large ones, or vice versa. For decades, there were debates on this topic, mainly led by American and Soviet scientists. The former favored a bottom-up approach, while the latter favored a top-down approach. So let's delve into what the significant difference is here. In the bottom-up scenario, the universe began with strong fluctuations on small scales. Over time, these fluctuations grew into dense regions, eventually leading to the formation of clusters that grouped together and grew into large galaxies. According to this scenario, black holes formed first, along with large star clusters, and only much later did they evolve into what we now know as galaxies. Now, considering the other scenario, the universe began with strong fluctuations on large scales. On small scales, regions that were too dense experienced gravitational collapse, transforming from irregular ellipsoids into pancakes, which eventually evolved into galaxies. In this scenario, galaxies formed first, and black holes grew in their centers later. For a long time, there was no definitive evidence supporting either of these theories. However, everything began to change when we discovered and started measuring the residual radiation from the Big Bang, which provided us with a lot of information about the early universe's structure compared to the current one. Now, we are not interested in how the universe originated. Instead, we want to know which of the mentioned scenarios is correct. You probably know that the universe is primarily composed of dark energy and dark matter, with ordinary matter and radiation making up only a small percentage, less than 1% to be exact. At least, that's what we believe, either because it's true or because we're trying to soothe ourselves with scientific gaps we can't currently resolve within the universe. Our knowledge comes from a combination of evidence, primarily from background microwave radiation observations, the study of large-scale structures, and measurements of the universe at great distances. Here, you can see various energy components of the universe which are crucial for understanding cosmic evolution. Furthermore, we can learn about the universe's structure on large scales through baryon acoustic oscillations or the cosmic microwave background. This helps us understand the scales and patterns of initial universe fluctuations. Regarding the singularity before the Big Bang, we now have several questions. Did it happen on large or small scales, or did it occur simultaneously at all scales? These questions can be readily answered by studying the cosmic microwave background. Moreover, we will attempt to determine which part of these fluctuations is the result of gravitational and electromagnetic interactions that occurred since the universe's inception. The initial distribution of fluctuations, as shown in the Blaine variant, was with respect to scales. This means that fluctuations of roughly equal strength occurred at all scales, both large and small. The distribution of oscillations on the right side of the graph became as such due to the interaction between dark matter, ordinary matter, and radiation, driven by gravity. However, it's the flat left portion of the graph, corresponding to large scales, that reveals the absence of a curve. This suggests that, in conjunction with the data from the right side of the graph, the universe was born with fluctuations of roughly equal strength at both large and small scales. This fact has been known for over 10 years now. The most recent projects have only confirmed our assumptions. Now, after hearing all this, you may still find the answer to the question elusive. However, there is another piece of the puzzle that sheds light on the formation of structures in the universe and may provide us with a precise answer. Despite the existence of structural precursors at all scales that contribute to the development of events from top to bottom, the speed at which gravity propagates in the universe plays a crucial role. High-density regions on small scales can attract additional matter relatively quickly because gravity travels at the speed of light. On the other hand, structures on large scales cannot change rapidly. Those with sizes on the order of tens of millions of light years must wait tens of millions of years to feel the force of attraction. In other words, both top-down and bottom-up scenarios play a role, but the bottom-up scenario gains an advantage of millions of years. The first stars in the universe began to form no later than 100 million years after the universe's birth, or the onset of a new cycle. Among these early stars, which formed from primordial hydrogen and helium, there were massive ones that would eventually become the first black holes in the universe. This process remains consistent over time. When a massive cluster of new stars arises, the heaviest ones, typically blue and hot, end in catastrophe. In extreme cases, these stars can have masses hundreds of times greater than that of the Sun, resulting in the creation of very large black holes. Just a few million years after their formation, these black holes can exist. Therefore, as far as we know, stars and black holes formed first in the universe, and galaxies appeared around them through the aggregation of these small regions. Over time, they grew into supermassive black holes and large galaxies that we observe today. However, this required initial fluctuations in power comparable on both large and small scales. So, the best answer to our question is that the seeds of supermassive black holes in galaxies formed first, roughly around the same time. These black holes were initially quite substantial and had grown to 1,000 times the mass of the Sun before their surroundings could be called galaxies. Thus, it turns out that black holes formed first, but in the regions that eventually became galaxies. This is the correct answer. The event horizon of a black hole is a spherical or nearly spherical boundary from which not even light can escape. However, there is a prediction that outside the event horizon, a black hole emits radiation. It's challenging to imagine considering the diversity of forms matter takes in the universe. For millions of years, there were only neutral hydrogen and helium atoms. Similarly, it's almost as difficult to fathom that someday, trillions of years from now, all stars in the universe will burn out, and only remnants of the currently vibrant universe will remain, including the most impressive objects, black holes. However, black holes are not eternal either. Today, we will embark on a mind-boggling journey and try to understand what happens when a black hole ceases to be a black hole due to Hawking radiation. To answer this question, it's important to understand what a black hole truly is. Black holes primarily form after the collapse of a massive star's core. Such stars have exhausted all their nuclear fuel and can no longer synthesize heavier elements. As the core's synthesis ceases, it experiences a significant drop in radiation pressure, which previously prevented the star from gravitational collapse. Meanwhile, the outer layers often undergo an uncontrollable fusion reaction and explode into a supernova. The core initially compresses into a neutron star, but if its mass is too great, even neutrons collapse, forming a dense state that gives rise to a black hole. Black holes can also form when a neutron star, in the process of accreting enough mass from a companion star, crosses the threshold required to become a black hole. From a gravitational perspective, all that's needed to become a black hole is to accumulate enough mass in a sufficiently small volume so that light cannot escape from a particular region. Every mass, including our Earth, has its escape velocity, the speed required to escape gravitational attraction at a certain distance from the center of mass. We'll call this r. It determines the size of a black hole's event horizon, the distance from the center of mass where the escape velocity equals the speed of light. But what happens inside this region is less well known. All matter within this region must collapse to a singularity. It may be tempting to imagine a state of matter that allows it to remain stable and have a finite volume within the event horizon, but this is physically impossible. To exert an outward influence from within, particles must send carriers of interaction in that direction, away from the center of mass and toward the event horizon. However, these carriers of interaction are also limited by the speed of light. It doesn't matter where within the event horizon these interactions occur, because all world lines end at its center. However, for slower and more massive particles, the situation is even worse, because as soon as a black hole with an event horizon appears, all matter inside it collapses into a singularity. And since nothing can escape, one could conclude that a black hole is eternal, if not for quantum physics. In quantum physics, there exists a non-zero amount of energy inherent to space itself, i.e., the quantum vacuum. In curved spacetime, the quantum vacuum acquires slightly different properties than in flat space, and there are no regions where curvature is higher than in the vicinity of a black hole's singularity. Therefore, if we compare these two laws of nature, quantum physics and spacetime, from the general theory of relativity around a black hole, we obtain a phenomenon known as Hawking radiation. The visualization of quantum chromodynamics demonstrates how particle-antiparticle pairs arise from the quantum vacuum in very short periods of time, as a consequence of Heisenberg's uncertainty principle. If you perform calculations according to the quantum field theory in curved space, you will get a quite astonishing result. Thermal radiation emanates from the space surrounding the black hole's event horizon. The smaller the event horizon, the stronger the curvature of space nearby, and the higher the rate of Hawking radiation. If our Sun were a black hole, its Hawking radiation temperature would be 62 nanokelvin, whereas a black hole in our galaxy would be as low as 15 femtokelvin. This is only a tiny fraction of 1 for a black hole. This means that small black holes evaporate faster, while large ones live longer. But the most astonishing thing in all of this is that, until the very last fraction of the last second, a black hole will maintain its event horizon until its mass becomes zero. However, the last seconds of a black hole's life will be characterized by a unique and very massive release of energy, and it will have just 1 second left when its mass drops to 228 tons. At that moment, the size of the event horizon will be 300 in the 40th power meters, which corresponds to the wavelength of a photon with energy exceeding anything achieved so far at the Large Hadron Collider. But in this last second, an enormous amount of energy, equivalent to 5 million megatons in TNT, will be released, creating the sensation that millions of nuclear bombs are detonating simultaneously in a small region of space. In this final stage of a black hole's radiation, as it shrinks in mass and radius, its Hawking radiation becomes increasingly higher in temperature and power. In this final stage of a black hole's radiation, as it shrinks in mass and radius, its Hawking radiation becomes increasingly higher in temperature and power. One of the most popular topics discussed in the scientific community is undoubtedly the subject of black holes. The thing is, black holes are not formed solely from the collapse of very massive stars. Supermassive black holes also exist at the centers of galaxies, with masses millions or sometimes billions of times that of the Sun. Such a black hole is presumed to exist at the center of our galaxy. However, no matter how much you want to, and no matter what technologies you use, so far it can only be observed indirectly. So let's try to understand how close we need to be to a black hole to see it, and whether it's even possible to see a black hole, specifically how it works. But first, let's clarify how we know about the existence of a black hole at the center of our galaxy. The thing is, visible light contains a lot of dust in the plane of the Milky Way, effectively blocking our view of the galaxy's center. However, in other wavelengths, such as infrared, X-ray, or radio, we can see through the dust and discover many interesting things. There's hot gas, moving at tremendous speeds, as well as flashes corresponding to matter being absorbed by the black hole. Most interestingly, the orbits of individual stars revolve around the same point, one that doesn't emit any light at all. These facts are consistent with the presence of a supermassive black hole with a mass of 4 million times that of the Sun. And the more massive a black hole is, the larger, or more precisely, the physically bigger its event horizon is, the region around it from which light cannot escape. If our Earth suddenly turned into a black hole, its diameter and event horizon would be only 1 7/10 of a centimeter. The diameter of the event horizon of a supermassive black hole at the center of the galaxy is 23.6 million kilometers, or 40% of the size of Mercury's orbit around the Sun. Moreover, in other galaxies, according to scientists' assumptions, there are even larger black holes. They are just millions or thousands of light years away. The thing is, for an individual object, this is a very large size, and the effect of general relativity that causes space to curve only increases it. But even though the size of this object is gigantic, it is extremely far away from us, which makes it very difficult for us to observe. At a distance of 26,000 light-years, the visible size of the black hole would be only 19 angular microseconds, or 19 millionths of a millionth of a degree. To put this into perspective, the Hubble Space Telescope's resolution is 26 angular milliseconds, which is more than 1,000 times larger than what is needed to see this black hole. In theory, if we were to get closer to it, at a distance of a few hundred light-years, we could see it directly. But, as you might have guessed, this is unfeasible. However, we have one technology that can bypass this limitation. In certain long wavelengths, particularly in radio and X-rays, a black hole can occasionally flare brightly, or objects passing by it can illuminate the event horizon from behind. The maximum resolution is determined by the size of the telescope's mirror. How many wavelengths can fit across that mirror? For radio telescopes, these wavelengths can be several meters long, so huge telescopes are needed to achieve high resolutions. But there's a workaround for achieving higher resolution without the need for building a telescope the size of the Earth. This workaround involves using an array of telescopes separated by very large baseline distances. They would gather light like a single, regular telescope. The object would still be quite dim, but their resolution would be the same as a telescope, with a mirror diameter equivalent to the distance between the farthest telescopes in the array. This idea is being implemented by the Event Horizon Telescope project, which plans to use large baseline distances for short wavelengths, precisely for the measurement we are interested in. However, there are a few assumptions. An array of 7 or 13 stations, each of which would answer the question if a black hole has a real event horizon observed directly. The black hole in the center of our galaxy, Sagittarius A*, is an ideal target for scientists, and it is expected to have the largest event horizon visible from Earth. Interestingly, the second largest should be located at the center of M87, the largest galaxy in the Virgo cluster. Its size will be 5 times larger than the maximum resolution of the Event Horizon Telescope. This means that we will be able to closely examine its jet and understand how these supermassive objects behave. However, when it comes to observing a black hole with the naked human eye, I must disappoint you because the resolution of the human eye is trivial. It's only 60 arcseconds. In other words, to observe something with a visible size of 19 angular microseconds, you would need to be 3 million times closer to it, which means you'd have to approach it at a distance of 546 astronomical units. The closest star to us, besides the Sun, is Proxima Centauri. It is located at a distance of 4.2 light-years, or 268,000 astronomical units. So, you would need to be 500 times closer to the black hole than the closest star to us to see anything. This is just to give you an idea of how challenging it is. In reality, this is not the last word on black holes. They are objects of heightened interest among scientists worldwide because any fresh news about them instantly becomes popular among space enthusiasts. Black holes are the most compact and simplest objects in the universe. They are described by just 2 parameters, mass and rotation speed. From an astrophysical perspective, black holes represent the final stage in the evolution of stars. For example, a massive star evolves, explodes, and its core compresses into a black hole. The event horizon of a black hole is a boundary, a shell with no physical surface. It's just a distance from its center, a point beyond which an object or light can't escape, due to the very strong gravity that prevents anything from leaving. Mathematically, leaving the event horizon implies moving backward in time, which is impossible according to physics. Today, we'll identify the black holes closest to Earth and discuss recent discoveries. You'll also learn how to see a black hole from Earth without a telescope. For a long time, black holes were thought to be products of various theorists' imagination. Even our channel received a flurry of emotional comments until this famous image came along. Mention of black holes was made in the theory of general relativity back in 1916. However, the first cosmic discovery related to black holes happened only 56 years ago with Cygnus X1. It was discovered in 1964 and is one of the brightest sources of X-ray radiation, boasting the highest flux density. Cygnus X1 was the first X-ray source identified as a candidate for a black hole. It's among the most studied objects, and we know that its mass is nearly 15 times that of the Sun. It's demonstrated that this object is too compact to be anything other than a black hole, with an event horizon radius of approximately 26 kilometers. At one point, there was debate about Cygnus X1. For example, until 1990, the renowned scientist Stephen Hawking didn't believe it was a black hole. However, he later conceded when observation data solidified confidence in the presence of a gravitational singularity in this system. Furthermore, we've detected X-ray and radio emissions from the centers of galaxies, indicating the existence of supermassive black holes even without visible cosmic objects. We've identified dozens of black holes directly through their gravitational waves. Now, let's discuss the nearest black holes to us and what recent discoveries have revealed. In the center of our Milky Way galaxy, in the constellation Sagittarius, approximately 25,000 light-years away, lies the closest supermassive black hole. A smaller black hole, around 5 solar masses, orbits a sun-like star at a distance of just 3,000 light-years from Earth. Geographically, this is in the Unicorn constellation. Another nearby black hole was recently discovered, breaking distance records. It's in a triple system called OJ 68+19, located in the southwestern part of the constellation Telescope near the borders of the Peacock and Altar constellations. Due to its location, the system can only be observed south of 33 degrees northern latitude. The system appears as a variable star faintly visible to the naked eye. It's 1,120 light-years away from us and is moving away at a speed of 9.4 kilometers per second. In May 2020, it was announced that this system contains the nearest black hole to our solar system, making it the first instance of a black hole in a star system visible to the naked eye. Scientists were able to track the motion of 2 companion stars and deduce the existence of this invisible object. This system could just be the tip of the iceberg, suggesting that many more such black holes could be discovered in the future. What's even more interesting is that this black hole resides in a triple star system, which is quite rare. Most models of star evolution and supernova explosions predicted that such a system would be disrupted, with individual objects drifting apart. However, HR 68+19 continues to exist as a triple system, showing that this doesn't always happen. Lastly, this discovery confirms the theory that the Milky Way likely contains many more black holes than the few dozen that have been discovered so far. Scientists believe that since the formation of our galaxy, a significant number of stars have evolved into black holes at the end of their lives. The discovery of this quiet, invisible black hole in HR 68+19 opens up the possibility of finding many more black holes in our Milky Way. So, the topic of black holes is highly relevant today. Supermassive black hole is the largest known genius among scientists and probably the rarest celestial body. Supermassive black holes typically exist in one galaxy, but not in all galaxies. Hello everyone, here is where these supermassive black holes come from. Let's find out together, starting now. According to existing astronomy and physics, It is known that standard black holes appear when particularly bright and massive supernovas explode. Theoretically, the mass of these black holes ranges from 30 to 50 times that of the Sun, but in reality, there are many that are much lighter. Black holes with hundreds or thousands of times the mass of the Sun have not yet been discovered, and only a few candidates have been proposed. This is known as the intermediate mass black hole problem. The main character of this discussion is the supermassive black hole, which has a mass of tens of thousands to millions times that of the Sun. Its origin is one of the most interesting problems in astronomy and physics. In reality, there are no stars of this size, so where did they come from? The relationship between supermassive black holes and galaxies is also fascinating. These black holes are typically found in the center of galaxies, but the existence of galaxies without supermassive black holes is known. However, supermassive black holes without galaxies have not yet been confirmed. The formation of galaxies and supermassive black holes is a problem similar to the chicken and egg problem. Which came first, the supermassive black hole that gathered matter around it, or the galaxy that formed first and had a black hole at its center? There is still no consensus on this issue. So where did they come from? The biggest problem in the formation of supermassive black holes is that it is not enough for a massive amount of matter to gather at a single point. To increase the mass of a black hole by having a large amount of matter fall into its singularity, it must rotate very slowly. Otherwise, an accretion disk will form around the black hole, and that will be the end of it. Of course, it is possible that the matter in the surroundings could be consumed by a black hole, but it is not very common for it to become a supermassive black hole. To understand the most likely explanation for the formation of these supermassive black holes, we need to look back in time to the distant past, around 550 million years after the Big Bang, during a period known as the Dark Ages. During this time, the universe was filled with hydrogen and helium and was not yet transparent enough for light to pass through. It is believed that the first stars began to shine during the end of the Dark Ages and the following cosmic dawn. As the first stars appeared, matter was consumed and transformed into starlight, gradually making the universe more transparent and bringing it closer to its current state. Generally, the universe during the Dark Ages was a cradle of a giant star, meaning it was a gas or dust cloud where new stars were born. The existing theory is that dark matter actively participated in this process. As dark matter gathered material through gravity and began to surround it, galaxies were formed in no time. At the center of this fence, the density of material is very high, and it is said that primitive stars, which weigh more than 20 times the mass of the Sun, were formed massively at this time. For various reasons, these stars seem to have been very unstable and began to collapse rapidly without exploding. When a supernova explosion occurs, it collapses and becomes a black hole or neutron star. Although it is only a tiny fraction of the matter that was concentrated in the building, when a primitive star collapses, it becomes a black hole in its entirety. Then, these black holes merge, creating a supermassive black hole. Some modifications have been added to the theory through recent research. Many scientists currently believe that there was no merger between black holes, but instead a single primitive star with a vast mass, ranging from tens of thousands to millions of times the mass of the Sun, was formed in the galaxy. It is difficult to imagine what process might have taken place, since such stars do not exist in the universe today. Perhaps these primitive stars began to collapse silently for only a few thousand years. Although this hypothesis seems to make sense, there are several unexplained phenomena. One of them is, as mentioned earlier, that most of the supermassive black holes have masses of hundreds of millions or billions of times that of the Sun, not just thousands of times. For a black hole to become this massive, according to the hypothesis of a collapsing primitive star, it must absorb an enormous amount of matter in a very short astronomical period, many millions of times its own mass. However, in reality, black holes do not continue to grow infinitely because the surrounding matter is almost exhausted. The remaining matter becomes part of the accretion disk and does not fall into the black hole. The first black hole was hypothesized to solve problems with existing theories, and scientists attempted to use new theories, such as the primitive black hole theory. The key point of this theory is that some black holes were not originally related to stars and never were stars. These black holes are believed to have formed shortly after the Big Bang. At that time, the universe was very hot, dense, and rapidly expanding. In this situation, the space itself was moving in a different way from today. It is believed that the unevenness of space, or pockets of space distortion, may have compressed matter and caused collapse. There were various masses in these primordial black holes. The smallest black hole was only about the size of the Planck mass, which is very small at 1/1,000,000th of a kilogram. This type of black hole may have collapsed quickly and no longer exists. On the other hand, there is a possibility that the largest black hole was thousands of times the mass of the Sun. This is the type of black hole that we find most interesting. These primordial black holes had an incredible density of matter. There is a possibility that it absorbed a massive amount of matter in a short period of time and grew to a size close to that of a supermassive black hole, which then gathered surrounding matter and facilitated the formation of the first galaxies. Currently, no new primitive black holes, supermassive black holes, or new galaxies are formed in the universe due to changes in matter density. However, there are weaknesses in the theory. For example, in a very compact universe, a young supermassive black hole may have grown rapidly, but it is unclear why it did not absorb all or most of the matter. Additionally, it is unclear why the universe entered a dark age in this scenario. Matter did not just scatter throughout the universe, but rather it was originally gathered in galaxies. However, if we assume that the natural formation of supermassive black holes was possible not only immediately after the Big Bang, but also during the following 500 million years, we can solve this problem. Currently, there is no hypothesis that can explain why there are no supermassive black holes present in all galaxies. It is possible to guess that this could be due to a lack of matter in dwarf galaxies. But even in the Triangulum galaxy, the largest in our local group, there are no supermassive black holes. Therefore, a theory that can explain all of these phenomena will emerge in the future. What would happen if there were a black hole in our solar system? First, let's clarify the concept and numbers a little. Known black holes are formed by a vast amount of matter collapsing into a small space, most often from a star, including very massive stars. The typical mass of a black hole that astronomers have been able to detect is at least 3 to 5 times that of the Sun. Of course, if there were such a black hole where we could stand, we wouldn't be orbiting around the Earth. Instead, the Earth would become its satellite, orbiting around it. But in theory, any amount of matter could be compressed into a singularity, creating a black hole. Therefore, for the purposes of this video, we will assume that our hypothetical black hole has a mass similar to that of the Moon. How could such an object come into being? It could be born from some anomaly, or it could have been born for an alien experiment. More accurately speaking, the event horizon of a black hole is very small, about 0.1 millimeters in size. Earth is not sucked into it because black holes behave the same as celestial bodies with the same mass. However, its effect on Earth is very interesting. To talk about the effect of such a black hole on Earth, it's best to start with something simple. For example, let's start with the appearance of the night sky. A black hole with stellar mass would have a bright accretion disk surrounding the black sphere, creating a very beautiful spectacle. You might have seen this kind of image in an illustration, science fiction movie, or computer game, but please forget about the image this time, as it doesn't apply in the case we are discussing, as I mentioned earlier. Black holes with masses similar to the Moon are very small. They have a strong gravitational force, but they are so small that at best, we can only see faint patches in the sky on a regular basis. In the worst case, it may not be until the space age that we realize the existence of black holes. Instead of solar eclipses, we may observe the Sun through a gravitational lens caused by a black hole. Light passing through the side of a black hole is distorted by its gravity. Therefore, when the Moon passes between the Sun and the Earth, we can briefly observe a faint distortion on the solar disk. Also, when the Moon is between a star and the Earth, the star that is the source of light appears differently to us due to the lens effect, such as appearing to emit momentary flashes like some other stars, or appearing to expand slightly. However, because black holes are so small, we can observe these phenomena only through high-performance telescopes. There is a deep connection between our culture and the moon, historically. The first calendar was likely the lunar calendar, no matter when it was made. The periodic changes in the size of the moon can be easily observed if there is only 1 month, but it is difficult to calculate it in areas where there are only rainy and dry seasons. If the moon were to become a black hole, the spirits would naturally become unknowable. This would cause a significant delay in the development of not only astronomy, but also civilization as a whole. In reality, time would only be measured in day and night, and it wasn't until the Stone Age that the concept of a year could be recognized. However, this is a story of when the Earth could somehow escape the destructive effects of a black hole, which may be quite difficult. As I mentioned before, this is the story of the eternal end. When a black hole appears nearby, it is very small compared to the many major changes that occur. As you know, it also affects the Earth's gravity, not just cars, but also constantly swirling to prevent other parts of the Earth from cooling down. Even if there is a black hole instead of the moon, there will still be tidal effects on the Earth, but because of its small size, the tidal effect appears to be concentrated in a narrower range and at a pinpoint. However, it will act more strongly. Near the equator of the Earth, natural disasters such as volcanic eruptions or earthquakes will occur intermittently. As a result, life will become practically impossible, and there will be a significant impact on the Earth's climate. Due to this geological activity, the Earth is getting warmer, and the transparency of the air is decreasing due to the continuous emission of volcanic ash. Earth will become darker and hotter in such an environment. Before we even consider whether humans can be born in such a scenario, it is unknown whether life can survive at all. It is entirely possible for Earth to become like Venus. Another problem is radiation emitted from the Earth's satellites. Black holes, in particular, emit severe radiation from their accretion disks. In this case, interaction with solar winds and the moon's magnetic field may also occur. Perhaps the Earth will be bombarded with constant streams of various particles, and it is unknown whether the Earth's magnetic field can protect it. If it cannot, after hundreds of millions of years of radiation exposure, all of the Earth's water will decompose due to the radiation's influence. Without radiation protection suits, the Earth will become an endless barren wasteland where nothing can survive. Of course, in such a scenario, no form of life could exist. Finally, there is a phenomenon called Hawking radiation, which suggests that any black hole will consume energy and mass over time and eventually evaporate. Particle pairs are created and evaporate, which is a very gradual process. For a stellar mass black hole, it would take endless time with dozens or hundreds of pairs sticking together, while a black hole with the mass of the moon would take only billions or trillions of years. In theory, the smaller the mass of a black hole, the more actively the particles mentioned earlier are created, causing another problem for us. As the particles rain down on Earth, they create confusion in the magnetic field and cause geomagnetic storms one after another until the last one explodes and dies. Of course, that is if it hasn't been swallowed by another black hole by then. There is also a theory that there are many small black holes in the universe, which are considered as one of the candidates for the role of mysterious dark matter. These black holes are thought to have emerged after the Big Bang because they have certain properties that satisfy the matter and space. If this hypothesis is correct, theoretically, it is also possible for Earth to have such a satellite. Lastly, there is something I would like to say. The possibility of such satellites being born in the solar system is low. In such cases, black holes will swallow all matter in the gas and dust cloud phase and grow to become a normal mass black hole. However, there is a good chance that they may come from somewhere in a completed star system far away. Certainly, there has never been a similar phenomenon observed in an alien planet. Therefore, the possibility of such an event occurring seems low. What was before the Big Bang, from which our video now starts, you can easily remember by simply rewinding a bit, even from what your morning or this week began with. Though it may be a bit more challenging for some here, we are so accustomed to everything having a beginning that subconsciously we assume it for everything. However, what about something so old, even ancient, that its beginning cannot be found so easily? We've all heard about the Big Bang, but what preceded that event remains a mystery and nothing more than hypotheses. Despite the fact that the Big Bang theory is one of the most popular ones today, understanding it is not so simple. Moreover, it is crucial to remember that it is primarily a hypothesis, and we must consider the inaccuracies that scientists still need to eliminate with new astronomical observations and research. However, physicists have enough independent cross-data that makes the Big Bang theory the main starting point of modern cosmology. Everything around us is a direct consequence of an event that happened 14 billion years ago. According to the theory, space, time, matter, and energy were all confined in a fiery ball called the Big Bang. It expanded, and from its cooling debris, galaxies formed, including our Milky Way, one among approximately 2 trillion. The idea that the universe emerged from nothing was so insane that scientists were skeptical for a long time. However, existing evidence was convincing enough. Galaxies are moving apart like cosmic fragments, and the heat of the Big Bang still surrounds us in the form of cooled cosmic microwave background radiation, discovered by radio astronomers in 1965. Today, scientists assume that all processes after the Big Bang were driven by the gradual cooling and thinning of the universe. As we know, temperature is a measure of particle motion, and as the temperature dropped, particles slowed down. The slower the particles move, the easier it is for them to come together. As the universe cooled down, initially flying quarks could merge into protons and neutrons and other hadrons and leptons. Then, the particles that had been obtained, continuing to slow down, began to form the first nuclei of familiar atoms, and so on. However, precisely what the universe was like during the Big Bang cannot be said with certainty. We can only assert that it was incredibly dense, and this changed over time. Everything we observe around us was incredibly tightly packed into a very small space in the beginning. But how can it be both infinite and at the same time so small? When people read about the theory, they might imagine that the universe was first smaller than an atom, then the size of a football, and so it expanded over 14 billion years. However, this analogy assumes that space initially had boundaries and an edge, but nothing suggests that the universe was not infinite even at the time of the Big Bang. Before that, it was smaller, and the object that occupied a square meter of space has now expanded to billions of light years. But even at the very beginning, the universe had no boundaries. Here's how it's explained by Professor Uriam Rocknes, a theoretical physicist at the University of Oslo. The entire observable universe comes from a tiny region that can be called a point, but nearby regions also expanded, and so did the next ones. Some of these regions are now so far away that we cannot observe them. If we think of the Big Bang as an explosion, it might seem like it started from a specific point at the center. However, when it comes to the birth of the universe, almost all galaxies are moving away from Earth in all directions. Therefore, Earth was never and will never be the center of the universe. Any observer on any other planet will also see galaxies moving away from them. In other words, the universe is expanding everywhere simultaneously. According to the inflationary model, the universe shortly after its birth experienced a very short period of exponential expansion, doubling its linear dimensions many times over. Scientists believe that this process began around the time of the strong nuclear force separation. This expansion, popularly known as cosmic inflation, was extremely brief, lasting only about 30 seconds. However, it increased the size of the universe by at least 10 to the 30, a billion times, possibly even more. But what if we want to look even further back in time, before the Big Bang? The main answer comes down to the fact that before the Big Bang, there was nothing at all. It means that the universe originated from nothingness, which is impossible even to imagine. When and why such a thing could have happened remains beyond comprehension. However, scientists insist on their position. Among them is the renowned theoretical physicist Stephen Hawking from England, who says that they didn't just imagine that the universe came from nothing. They arrived at this conclusion through rigorous mathematical calculations in which no one has found any errors. At some point in this mysterious nothingness, there might not have been familiar forms of matter, but it was not entirely empty, and certain processes might have been occurring that could give rise to small explosions. Ultimately, the Big Bang happened. To find evidence of this hypothesis, researchers try to create something similar to nothingness. They build special chambers from which they remove particles of matter and lower the temperature, almost reaching the coldness of space. Surprisingly, the resulting nothingness turns out to be something that can be studied in various ways. Here, we can think of vacuum energy and zero-point energy, but that delves into quantum mechanics, which would require much more time to explain. Still, many people disagree with the idea that the universe originated from nothing. Opponents of this hypothesis answer the question of what was before the Big Bang in various ways. Even though we know that the universe existed before the Big Bang, there is still very little that we can say about the nature of this ancestor of our universe. However, it can be assumed that something in its history led to a Big Bang, giving rise to our universe. Of course, there are other opinions. Perhaps before the Big Bang, there existed a universe similar to ours, or maybe entirely different. It is also possible to speculate that before our universe, there were at least two other universes whose collision led to the Big Bang. One can even imagine that the universe exists eternally, and in its history, Big Bangs alternate with big collapses. Such explosions could occur if the expansion of the universe changed to contraction. Finally, it can be assumed, and many agree, that at the initial moment of our universe's history, an incredible event occurred. The newborn universe rapidly expanded and inflated to enormous proportions, giving rise to bubbles in which different universes grew one after another. This way, a large universe emerged, also known as the mega-universe or multiverse. If this is true, just as our galaxy is one of billions of galaxies known to us today, our universe is one of many completely unknown other universes. But the most interesting, in our opinion, is the conformal cyclic cosmological model, abbreviated as CCC. According to this theory, the life of the universe consists of epochs, and each epoch's exponential expansion ends with a Big Bang, becoming a precursor for the next epoch. What would happen if one squeezes the distant future in the mathematical model of the universe, representing infinity as a finite boundary? What if the singularity of the Big Bang is stretched to the same smooth, finite initial boundary? According to the model, the universe goes through infinite cycles, where in each preceding cycle, the time in the future tends towards infinity, which becomes the singularity of the next cycle. It is assumed that the masses of all particles in the universe constantly and steadily decrease to zero over time, thereby increasing the energy. Additionally, an interesting assumption is that supermassive black holes, which are now detected at the centers of many galaxies, are relics inherited from past universes into our own. Professor Penrose's theory is fascinating, and we highly recommend exploring it. The cyclic theory exists in several versions, just like the inflation theory, and according to Professor Paul Stanford, the differences between them are purely technical and only interesting to specialists. The general concept remains unchanged. First of all, in our theory, there is no moment of the world's beginning, no singularity. There are periodic phases of intense birth of matter and radiation, each of which, if desired, can be called a Big Bang. However, each of these phases signifies not the emergence of a new universe, but merely a transition from one cycle to another. Space and time exist before and after each of these cataclysms, so it is entirely reasonable to ask about the state of affairs 10 billion years before the last Big Bang, from which the history of the universe is counted. The second key difference is the nature and role of dark energy. The inflationary cosmology did not predict the transition from decelerating expansion of the universe to accelerating expansion. However, when astrophysicists observed distant supernova flashes, standard cosmology didn't know what to make of the paradoxical results. The hypothesis of dark energy was proposed to reconcile these observations with the theory. Our approach is more internally consistent since dark energy is present from the beginning, facilitating the alternation of cosmic cycles. Nevertheless, as both Pohl and Steinhardt note, cyclic theory has its weaknesses, particularly in explaining the collision and bounce of parallel branes, i.e. lower dimensional spaces, from M-theory strings that occur at the beginning of each cycle. Other aspects of cyclic theory are better developed, but there are still many uncertainties to resolve. In conclusion, let's recall the following. Because events preceding the Big Bang have no consequences for observations, they can be excluded from the theory, and we can consider that time began with the Big Bang, as Hawking asserted. However, scientists still harbor hope of learning what existed before the beginning of time. Perhaps it was something grand or very dense, something that transitioned to us from another universe. There are more questions than answers, and for now, humanity is in search, and maybe someone among you will be able to tell the world what happened before the Big Bang. Have you ever wondered how our planet, our sun, and our galaxy came to be? Until recently, the universe was considered eternal, and its existence didn't trouble scientists. Albert Einstein even assumed the universe's eternity in his hypotheses and adjusted the equations of the theory of relativity accordingly. However, with the acceptance of the concept of the Big Bang, everything changed. Experts show that we live in the expanding and cooling remnants of a cosmic lump of matter. But what caused this initial explosion, and what preceded it? Did anything precede it at all? These questions are undoubtedly within the scope of science, but every attempt to answer them faces seemingly insurmountable obstacles, the infamous singularity, an infinitely small and dense point in which the entire universe, all the physics of the world, constants, matter, space, and time were compressed. Then, or during this event, the Big Bang happened, and everything listed above came into being. Nowadays, physicists have discovered the cosmic microwave background and started contemplating the very beginning. It's all a bit tangled, isn't it? The question remains, what was the problem with the existence of the cosmic singularity? It is one of the most serious problems in physical cosmology. The issue is that any information we have about what happened after the singularity can't provide us with any insight into what happened before it. Even now, so-called new physics leads us to the realization that our knowledge of the universe is still in its very early stages. Thus, at this moment, we can only talk about what we are capable of seeing with our eyes or through mathematical models on paper. One of the most frequently asked questions is, where exactly did the Big Bang occur? If there was an explosion, there must have been an epicenter. However, the reality is that our universe has no center. It is more accurate to imagine that the Big Bang occurred simultaneously everywhere in all points of the universe. Today, scientists assume that all processes after the Big Bang were influenced by the gradual cooling and decreasing density of the universe. As we know, temperature is a measure of particle movement, and as the temperature dropped, particles slowed down. Slower moving particles made it easier for them to interact with one another. During the universe's cooling, individual flying quarks merged to form protons, neutrons, and other hadrons and leptons. Then, these particles, continuing to slow down, began to form the first nuclei of familiar atoms. This period of the formation of the first atoms in the universe is called primordial nucleosynthesis, which lasted about 20 minutes after the Big Bang. During this period, the entire universe was heated to the state that we observe today inside stars. In this period, hydrogen and helium nuclei primarily formed in a ratio of 3:1, and these proportions of hydrogen and helium remain the two most abundant elements in the universe to this day. After the first nucleosynthesis, new atomic nuclei were hardly formed anymore, and the universe still remained hot, with matter existing in a plasma state. Electrons flew independently from nuclei, making the universe opaque to light. Photons constantly collided with electrons and couldn't travel straight, as if they were trapped in a mirrored labyrinth. This is why, by the way, you cannot see them through a daylight lamp or through our sun, which are also made of plasma and are therefore non-transparent. The universe continued to cool, and after about 300,000 years after the Big Bang, the temperature dropped sufficiently for electrons to join atomic nuclei. As a result, the universe became transparent. This moment is called recombination. The photons that filled everything around were no longer obstructed by electrons and could travel straight, instantly in all directions. Actually, these photons released at the moment of recombination are what we see today as the relic radiation of the cosmic microwave background. Next, the formation of the first stars occurred. It is assumed that these were very massive stars with a short lifespan that did not survive to our times. The first quasars, galaxies, and galaxy clusters and superclusters were formed. Subsequently, the formation of the interstellar cloud, which gave rise to our solar system, gradually occurred. Around the young sun, a gas-dust cloud formed. It should be noted that this disk was a remnant of the cloud from which the sun itself emerged in its early stages. This cloud gained rotation, which led to the formation of a rotating, flattened disk instead of a spherical one. At the beginning, the disk was 98 to 99% composed of hydrogen and helium, and the remaining elements were present in negligible amounts. However, it is precisely with their presence that the origin of planets is associated today. As the cloud cooled, refractory substances such as iron, silicon, titanium, nickel, their compounds, and others began to condense into dust particles. Condensation means transitioning from a gaseous state to a solid or liquid one. In the planetary cloud, there were no suitable conditions for most substances to exist in a liquid state, so gases heavier than helium and hydrogen immediately formed solid particles, bypassing the liquid phase. An example of this behavior can be seen with water vapor on Mars. Due to the relatively large mass of dust particles, they tended to gain more stable movement, moving toward the center of the disk. Gradually, a thin dusty disk formed inside the thick gas-dust cloud. With cooling, the number and size of dust particles increased, and the density of the dust disk increased. The rest of the initial disk became increasingly sparse. Eventually, the dust disk became many times thinner than its diameter. The composition of this dust disk was different in its different parts and depended on the distance from the sun. The inner regions, heated by the central star, cooled down, and more substances could form solid particles. For example, water vapor could transition into ice, probably somewhere around Jupiter's orbit and further away from the sun. At the same time, the solar wind blew lightweight gas molecules from the inner parts of the solar system faster than from the outer parts. As a result, gas almost left the regions close to the sun. The gradual cooling of the cloud facilitated the formation of countless compounds, mostly entering growing dust particles. According to the laws of physics, gases were more willing to condense on existing dust grains and less eager to form new ones. By the time the formation of the thin dust disk was completed, its density was tens of times higher than the surrounding gas density. The sizes of solid particles reached several centimeters, and the disk became gravitationally unstable. Random compressions in the disk did not dissipate, but on the contrary, kept recurring. This process culminated in the formation of millions of bodies several kilometers in size, which became the embryos of planets. They were named planetesimals. The composition of these planetesimals varied according to temperature conditions and the initial disk density, which, as we mentioned, depended on the distance from the sun. During the next several hundred million years, the largest planetesimals grew, accompanied by the destruction of smaller ones. The small planetesimals were also ejected from the solar system due to the gravitational influence of the massive planets. The fastest growth was observed for Jupiter, as it was situated in an area where icy water particles had already formed. These icy particles contributed to Jupiter's rapid initial growth. Another important factor that gave Jupiter an advantage over other giant planets was its closer proximity to the Sun, where the dust disk's density was higher. The embryos of Saturn, Uranus, and Neptune lagged in growth compared to Jupiter due to the lower density of the disk in their formation regions. Jupiter managed to accrete a vast amount of gas while it was not yet swept away by the solar wind. Today, we see that Jupiter is the most massive planet among all the others combined in the terrestrial group. Though they formed in the densest regions close to the Sun, they couldn't become the most massive planets in the solar system due to high temperatures and dense solar wind streams. Solid particles formed with less enthusiasm, and heavy substances like iron and silicon were in the minority in the initial cloud. As a result, the solar system got small planets near the Sun, mainly consisting of silicon, iron, and their compounds. Among these planets, only Venus and Earth have sufficient mass to retain an atmosphere, which consists primarily of heavy gas molecules that move less rapidly. Therefore, the Moon and Mercury have almost no gaseous envelope, and Mars has already lost almost all of its atmosphere. During the formation of planets, smaller particles collided with each other. If such a collision occurred near a future planet, the colliding bodies could lose so much velocity that their orbit around the Sun became impossible. They were influenced by the massive planet's gravitational pull and became involved in its rotation. This way, rotating swarms of particles formed around large planets, a fate resembling that of the dusty disk. Soon, satellites began to rotate around planets, following the galaxy's perception of time. Another hypothesis states that planets were never molten spheres. According to this view, they originated from the gas and dust nebula surrounding the Sun, gradually condensing into a gas-dust disk, which eventually fragmented into separate parts. Some of these condensations grew to the size of planets. For example, our Earth formed from its embryo in approximately 100 million years. During that time, enormous meteorites falling on it heated its depths and left numerous craters on its surface. Later, the air and water erased most of the craters on Earth's surface. However, on other celestial bodies where these essential components didn't arise, such as Mercury or Mars, the craters remained intact. Moreover, the study of planets beyond our solar system revealed discrepancies that raised doubts about the hot disk hypothesis. Some of these inconsistencies were related to the class of planets known as hot Jupiters, which have orbits close to their stars with periods of a few days. Astronomers made adjustments to the hypothesis to address these questions, but it didn't solve all the problems. Thus, for now, we have to be content with theories that, while not complete, can partly explain the origin of everything related to the surrounding space. Perhaps a new physics will offer the world of scientists who can explain ancient processes in a new light. Stars, planets, and cosmic matter, bound together by gravitational forces, form some of the most massive objects in the universe, galaxies. The exact number of galaxies remains unknown, but it is estimated to be several hundred billion, and that's only within the observable part of the universe. Despite galaxies being astronomically distant from one another, they sometimes collide. Such collisions are truly spectacular events on a grand scale. Cosmic evolution. In the universe, there are galaxies orbiting around a common center of mass. In such systems, there's a central giant galaxy with several satellite objects. During their evolution, if the orbits of smaller galaxies do not match, they all start to revolve around this center. However, if galaxies have identical orbits, they will merge into one large system, while the smaller object gets torn apart. Astronomers observe such collisions quite frequently. It is believed that the Andromeda galaxy also collided with a smaller galaxy in the distant past. Similarly, our system has also absorbed smaller galaxies. But if astrophysicists claim that the universe is expanding, why do galaxies collide? And all because the expansion of the universe is happening slowly. Galaxies in clusters and superclusters experience gravitational attraction towards each other and move at speeds of hundreds of kilometers per second. The cosmological expansion reaches such magnitudes only at distances of tens of millions of light years, which is hundreds of times larger than the sizes of galaxies. Therefore, within clusters, galaxies do not notice the expansion of the universe. They move and collide as if it doesn't exist. However, no matter how common such interactions may be, astronomers rarely manage to capture dynamic images of colliding galaxies, like the ones Hubble captured. ARC 282 consists of the spiral galaxy NG69 and its smaller companion IC 1559. They both have highly active cores, serving as powerful sources of radiation. The activity of ARC 282 is associated with the black holes located at their centers. Tidal interaction processes have led to a redistribution of matter within the galaxies, providing the black holes with abundant food. The galaxies have also formed a connecting bridge, which is visible in the Hubble image, consisting of elongated gas and dust affected by tidal forces. And that's not all. The Hubble Space Telescope also took a series of photos of two merging galaxies in the VV689 system, which astronomers have named the Angel's Wings. Unlike random visual alignments of galaxies that only appear to interact from Earth's perspective, these two galaxies in VV689 are in the midst of a collision. This galactic interaction has made the VV689 system in the constellation Leo nearly symmetrical, and now they resemble huge galactic wings. Another well-known space telescope, the James Webb, also captured interesting images. The star cluster in the Cartwheel Galaxy was formed as a result of a collision with a satellite galaxy. The Cartwheel Galaxy has two rings that expand outward from the collision center, much like ripples in a pond after a stone is thrown in. Due to these distinctive features, astronomers refer to it as a ring galaxy. It has a less common structure compared to spiral galaxies like the Milky Way. In the next two galaxies shown in the cosmic image, they pass through each other, leaving a bridge of young blue stars between them. The head-on collision between the two galaxies showcased an object of triangular shape where thousands of stars were born. This image was captured by the Hubble Space Telescope, as reported by NanoWork. Astronomers speculate that the galaxies passed through each other, triggering a fiery burst of star formation in a unique shape in NGC 2445, where thousands of stars ignite. This galaxy is rich in gas, the fuel from which stars are created, leading to its star-forming abundance. However, the new galaxy has not managed to escape the gravitational grip of its partner, NGC 24. The galaxy has pulled gas from NGC 2445, creating the peculiar triangle of newly formed stars. As we can see, these interactions can appear stunningly beautiful. In the search for dark matter, but it is not only the beauty that fuels scientists' curiosity. As early as the 1970s, serious arguments emerged in favor of the idea that galaxies contain so-called dark halos, apart from stars and gas. Theoretical arguments arose from considerations of the stability of the stellar disks of spiral galaxies, while observational evidence came from the large, non-decreasing rotation velocities of gas at the far edges of galactic disks, where there are almost no stars, and therefore the rotation speed is determined through gas observations. If the entire mass of a galaxy was primarily contained in stars, then the orbital velocities of gas clouds located beyond the stellar disk would decrease as the distance increased. This is observed in the planets within the solar system, where the mass is primarily concentrated in the Sun. However, in galaxies, this is often not the case, which indicates the presence of some additional massive and extended component whose gravitational field imparts high velocities to the gas clouds. The situation was partly clarified when massive dark halos were introduced into the mathematical model of galaxies. These dark halos do not contribute to the galaxy's overall luminosity and are only evident through their gravitational influence on the stellar subsystem. One way to obtain information about the structure of dark halos is by studying extended structures that form around galaxies during their interactions. For example, sometimes, during a close passage, one galaxy steals gas from another, winding it around itself in the form of an extended ring. The existence of extended polar rings can only be explained if the mass of the dark halo is approximately twice that of the luminous matter in the galaxy. Tidal tails also serve as reliable indicators of the presence of dark matter in the peripheral regions of galaxies. Perhaps the first evidence of hidden mass was obtained as early as 1933, when the astrophysicist Fritz Zwicky noticed that galaxies in the Coma cluster were moving faster than expected, implying the presence of some invisible mass that kept them from flying apart. The nature of dark matter remains unknown, so it is often referred to as some abstract cold dark substance that interacts with ordinary matter solely through gravity. However, due to its significant mass, it acts as the active background on which all scenarios of structure formation and growth in the universe unfold, while ordinary matter passively follows the proposed scenario. These ideas form the basis of the so-called hierarchical clustering scenario. According to this scenario, primary density fluctuations of dark matter arise due to gravitational instability in the early universe and then multiply by merging with each other. As a result, numerous gravitationally bound dark halos are formed, differing in mass and angular momentum. Gas collapses into the gravitational wells of these dark halos. This process is called accretion, leading to the formation of galaxies. The history of mergers and accretion of each dark matter clump largely determines the type of galaxy that emerges within it. The appeal of the hierarchical clustering scenario is that it describes the large-scale distribution of galaxies quite well. The most impressive numerical experiment conducted within this scenario is called the Millennium Simulation. Astronomers reported its results in 2005. In the experiment, the N-body problem was solved for 10 billion dark matter particles, starting from when the universe was only 120 million years old until the present day. During this time, nearly half of the dark matter had gathered into dark halos of various sizes, totaling about 18 million. Although complete and unequivocal agreement with the observations of large-scale structure has not been achieved yet, there is still much to discover. In 2002, a team of researchers led by Beth Willman began the search for unknown satellites of the Milky Way in the Sloan Digital Sky Survey. The first success came in March 2005, when a dwarf spheroidal galaxy was discovered at a distance of 300,000 light-years from us in the constellation Ursa Major. It became the 13th satellite of the Milky Way, with a record-low luminosity. All its stars emit light comparable to that of a single supergiant star, such as Deneb, the brightest star in the constellation Cygnus. The year 2006 turned out to be exceptionally fruitful for the discovery of satellites of our galaxy, when two other teams of researchers discovered 7 dwarf spheroidal galaxies around the Milky Way. And apparently, this is not the limit. Only recently, astronomers started to discover galaxies entirely devoid of dark matter or containing it in extremely negligible amounts. For example, the dwarf galaxy NGC 1052 DF2, which was discovered a couple of years ago by a team led by Peter van Dokkum from Yale University. Since then, several similar objects have been found, including DF4, located near DF2. These galaxies greatly puzzle scientists who are trying to understand how they could have formed without dark matter, or how they lost it. One hypothesis links their appearance to galactic collisions. In such an accident, the masses of their dark matter can continue their trajectory, passing through each other. However, clouds of ordinary matter experience pressure from each other, slow down, interact, and separate from the dark matter. This scenario is supported by an article published in the journal Nature by van Dokkum and his colleagues. Observations of DF2 and DF4 showed that the trajectories of these galaxies started to diverge from a common point about 8 billion years ago. Moreover, other dark matter-poor dwarf galaxies also started moving along with them. Today, DF2 and DF4 are part of a chain of about 7 to 11 such objects, located at a distance of about 70 million light-years from us. On the scale of star clusters, dwarf galaxies, and galaxies, collisions and mergers are constantly happening. Even our Milky Way is currently disrupting the Sagittarius dwarf spheroidal galaxy, which is its satellite. And in the future, this relatively small cosmic body, with only 1% of our galaxy's mass, will be completely absorbed. Looking further into the future, we can expect a collision and merger with the large Andromeda galaxy. According to scientists' predictions, the Milky Way and the Andromeda galaxy will collide in about 4.5 billion years. And quite soon, in 3 billion years, Andromeda will approach us so closely that the stars of its galaxy will be visible to the naked eye. What will this collision look like? Thanks to the Hubble telescope's image, we can now visualize what the merger of the Milky Way and Andromeda will look like from the outside. A group of 3 galaxies, collectively named NGC 7764A and located in the Phoenix constellation at a distance of 425 million light-years from Earth, serves as a model for this scenario. Scientists are already running simulations of the collision between the Milky Way and the Andromeda Nebula on supercomputers. Data indicates that the Milky Way has absorbed smaller neighbors in the past. For example, some dwarf galaxies and globular star clusters were destroyed by tidal forces and transformed into star streams, with their stars likely to be eventually absorbed by our galaxy. Using data from the Gaia Space Telescope, scientists partially answered the question of when the last collision and absorption of a neighbor occurred. Gaia creates a three-dimensional map of the galaxy by measuring distances to stars, enabling scientists to observe their movement directions. This led to the discovery that around 8 to 10 billion years ago, the Milky Way engulfed a sizable dwarf galaxy called Gaia Sausage Enceladus, GSE. As an inheritance from the collision, we received about 8 new globular star clusters along with 50 billion new stars. Additional research revealed that GSE was not a satellite of our galaxy, but was moving in a direction opposite to the Milky Way's rotation. Thus, our courses intersected and a collision occurred rather than a gradual merger. This intergalactic catastrophe provided us with material, forming about 50% of today's halo and 20% of the dark matter halo. The next similar event, as we mentioned before, will be the encounter with Andromeda. Scientists speculate that if the Andromeda Nebula and the Milky Way eventually merge, the resulting new galaxy will have an elliptical shape. It is even given a name, Milkomeda. By that time, the Sun, which might have transformed into a red giant, will be relatively far from the galactic center since the distance between stars will increase. However, this won't impact us anymore.